I can you see my screen?
No.
No? Can you see my screen?
Yes.
Which one do you see? Lecture?
Yes.
I'm not really familiar with how to share. This is weird. Oh, here. Do you see my face? My video?
Yes.
It's a corner? Right top corner? Oh, okay. And how can I go to share? Stop. I don't want a video. Stop video. Okay. Share. This is weird. Share. So do you see a crystal structure? Yes or no?
Yes.
Okay.
Professor Lee, I have a question real quick.
Yes.
Do you have a scheduled midterm yet? Do you know what day it'll be?
Oh, midterm. Oh, I didn't say that. I think after the spring break. Okay.
Okay.
Yeah. After spring. Yeah, I will talk about spring break. So let's see. 22nd. March 22nd, I think. Let's say. Okay. Let's.
Yep, thank you.
Yeah, if you have any problem, let me know. Okay. So today I will continue discussion. I'm using the copies of a book. Well, I purchased chapter 6. I'm author, but still, I need the electronic file, PDF. So the electronic Kindle version does not allow using PDF. That's my problem. I need a PDF so that I can write. Then I learned I have to buy chapter 6 in a Wiley. I paid $45. Oh my goodness. Just for chapter 6, I paid today. And then I was able to print out, even no PDF allowed print out and then scanned and the PDF. Wow. So that is really time consuming, but I need a book. Okay. So I did it. I just tell you what I did it. If you have question, you can raise question. Um, Previously, I just my file, not the book page. So maybe a problem. Students look at now is a matching with page, and everything is same as the book. Okay, it costly even. I purchased a couple of books. Oh my. So I like to move on. What was the last time? Um, I think, yeah, you can go over. This is pretty easy. Good examples, FCC, BCC, body, yeah, central cubic, body centered cubic, and then Miller. Uh, the Miller index is somewhat important in material science whenever they want to discuss from material, they need the uh, plane. So whatever they can define coordinate is based on the the yeah. Once they have a material, they have a coordinate. Okay, they know. Once I coordinate, then they can even say Miller index. From the coordinate. Okay, so index 1 1 1 1 1 is the same as this. No, no, no. 1 1 1 is this. Yeah, 1 1 1 is this. Okay. So they can define and discuss. Sometimes they use exact coordinate 0.98 1.1 something like that. You should understand. It is not the exactly one. Somehow, I don't know. They can do that, but we understand very close to 111. Now physics. Last time I just review photoelectric effect. This is so important. Okay. Before we discuss the material property, transport property, we call it material transport property, Seebeck, electrical conductivity, and thermal conductivity. Since these two are related, electron, okay, electron. So we have to, electron is the smallest particle and originally from atoms. And the K, we will discuss a couple of hours. I need to discuss K. Thermal conductivity is consists of electrical and um, lattice. Lattice is a smallest unit cell. It's a vibration. But electron, okay. I think I'm recording. Yeah. Yes, I'm recording. So it's very complicated. This is so important. Look at that. Z figure of merit is Seebeck and electrical conductivity and K. So anything, if upper 2 is good, the lower K is bad, then G is going to be bad. So the combination is a figure of merit. Okay, students, you really, if you have question, anytime raise a question. Okay. So these two we call I forgot the name, power factor or something like that. Okay, product of these two, power factor, I believe, because it's important electron. And then, but still, the thermal conductivity is partially electron. When electron is moving, then the energy is flowing because of electron. You know, electron is moving, then the energy, thermal energy, because the kinetic energy is moving. That's what happened. So pure vibration, you understand the thermal energy is this thermal energy. So we have to understand both. Okay, thermal energy. Well, thermal energy is everything, but the electrical consists of electrical and the lattice vibration. Electrical vibration, lattice vibration. Okay, so we're gonna for a while talk about the electron. What is the nature of electron? First, we discussed the light, and turns out light is a dual property, electromagnetic wave and particle, both. Okay, no question about it. The physicist demonstrated. Earlier, Maxwell demonstrated electromagnetic wave speed is a very close to the light speed. Not, I think, so close. So we start believing the light is electromagnetic wave. Yes. And then 1905, there is an experiment, Hertz, and they couldn't understand. And finally, it turns out very weird. Nothing to do with the energy of electron coming out. You know, we talk about the structure of nucleus and electron. So this is energy, and n equal 1. There is a orbit. You cannot see n equal 2, etc., etc. It can move depend on the energy. More energy, it can jump, excited. So it can be a free if you have enough energy. But the energy, they put a lot of intensity, it doesn't work. The only frequency change, a certain point electron coming out. That energy absorb energy and coming out. That's what happened. So this is exactly energy is Planck constant and frequency. This is we call photon energy. So photon appears now. Photon is a particle. The wave is wave. So photon energy is nothing more than the frequency. Yeah. So frequency, then look at that. Electron is coming. You can measure it. So exactly, and also energy a little bit. I was so curious. What is the nature of energy? It's very difficult to define, but one of energy is a digit, because here is energy and another energy. I think so. Energy between these is not happen anything. So something is a certain amount of energy, that is a photon. Certain amount of energy depend on the frequency, then electron is coming out. So it's only a particle um, or photon can photon can explain that. So now is a two dual property, and let me, yeah. Um, so that we set the energy. Okay. So what is the frequency of light? C is the speed. So that the frequency relationship, wavelengths, lambda is a wavelength, and c is the speed. Okay, so is the relay, and then frequency. And there is our ancestor try to understand the structure, rather for the they didn't know what is a structure, nucleus, uh, and electron depend on the atomic number. So they shoot some particle, okay, some particle shoot, and they learned actually. So they have some reflected, anything you can cover reflected. So if it is shoot, and then some goes straight, mostly, but some are, because they know the particle direction vector, are just diffracted. Some are backward. That was so. So that they say electron is so small. This is so heavy, proton, thousand times heavier to electron. So nothing electron can do effect. So it's just moving and pass electron and then bounce back. So they found actually nucleus. Actually, they found nucleus. And then later the Bohr's, this is the Bohr's model, and able to even calculate the radius, nucleus, and all kind of improvement. And then they able to calculate the radius, velocity. It turns, if it is only one atomic number, it is good, actually, very good. So hydrogen is we understand the agreement, and we calculate the kinetic energy, potential energy. The difference is binding energy. So we understand it's stable. the nucleus and the electron, because it's orbiting, there is an acceleration. It may be, there is a forces out, but actually it's balanced. So no, don't worry. Because of that, bonding energy is that. So when we look at the energy, G is a atomic number, electron, mass is all fixed. This is fixed. Only N depend on the N energy. So which means N, the ground state, or excited N2, N3, exactly depend on the N, and depend on the atoms. So this is so interesting. This is amazing. So for example, there is a frequency from the star. Listen carefully. That is a very specific frequency. Do you think you can calculate the energy? Say yes or no. I'm sorry.
Do that.
I said there is a frequency coming from star, unknown. Do you think you can calculate the energy?
Wait, the frequency is unknown? Or it's
No, known. Frequency is known.
Okay, it's known, then you can calculate it.
Yes. Calculate the energy. You can calculate energy. So this energy is this. So if the energy, because of light, we have a light from star. It is light. So what is a element? If this is energy, and there is only an element and the N. N is between this and this, or this and specific energy, because the light is coming, is how come is when the electron is moving to this is the N3, this is the N1, then this higher energy, this is lower energy, the light is coming out. Okay, this is a photon is coming out. That photon is, I believe, from star. So if you know the N1 and N3, so do you think you can figure out the Z, yes or no? Now.
How would you know the energy level?
The energy is the light coming from the star. So energy is known. Energy is known.
I'm talking about the specific energy level, N.
That is, you can try, okay? You can try, several try. So suppose N is all different, but and then once you figure out the N, then do you think you can figure out the element, yes or no? Suppose you know the N, then can you figure out?
If if you know it, yeah.
Yeah, if you know, yes. But that is there are, you can try, and then figure out actually. So that is a scientist, they can do it. We just don't have to do it here. So that's the way we can figure out the element, what element is from the star. And I think a little bit more. This is intensity and the frequency of though this is about visible 0.4, 0.7 is visible. This is temperature is a sun light, so it's about 5,000 K. This is the curve, and the curve this is 800. This is 300. The curve, okay. So it the black body curve, intensity curve. This is the light. That's why we can see this is a violet. This is a red. And since the 300K is no way they can illuminate the light. So, but it is about 1,000. They can start red if it is 1,000. It's very interesting. Okay, so light and temperature is associated. This is a micron. Micrometer. Okay? Wavelengths. So I think again, whole idea of the spectral analysis, laser again, when we control, this is simply we control the power. Okay, we control the power, illuminate. Let's say light. We control the light, and then we can control the electrons. Moving from here to here, whatever we can control. So the laser, I said, a lot of electron atoms, and then we control the light. So one just so strong laser we can create. Once we this is energy, is wavelengths we can control. So we can cohere, and then very strong. We can cut the steel plate or military use, melt. And it's a very control and unit frequency, very one frequency control, not like light. Light is a spectrum, all frequency. But laser is one wavelength, so powerful. It can shoot. Okay, it's a pretty simple. This is the idea of light and control the electrons. And then electron moving, not that this is not the electron. This is light is coming, light is coming. When is a move, light is coming. Okay, light is come. This is light, and then light is coming. But this is all kind of yeah, but something like that. So that so small tumor, 1 micron tumor, laser, and we can cure without damaging to other skin. So all kind of. So I think in this area they use these to figure out the material. Okay. And this is spectrum of hydrogen. This is spectrum of hydrogen. We know that light coming because of electron moving from a certain quantum number to lower quantum number is moving quantum number, and then light is coming. This is light, very clearly. Okay. So this is the equation actually you can use from initial final and the frequency. It's a very quite simple. I think I maybe some homework. So and the material, the solid, and once you have suppose atoms and material developed, then they want to know lattice constant, etc., etc. So how to do it is a laser. Shoot the laser and then reflection. And then we have a detected reflection and then see how is the structure of atoms. Okay, this is the technique they use to figure out the material. So it makes sense. The detail is light is not reflection. Some light is absorbed and then electron is coming and then some is reflect. So this detector sensing original reflection and some absorbed, some difference. The absorbed means orbit. If this light is coming, some light it is just a pass, nothing. But some is causing moving electron to lower, and then some light is coming out. So this is a very chaotic light if you don't control. So here is you can see what is the this structure behavior of atoms using the laser. A lot of technique. They call electron diffraction scanning, something like that. They use a scanning technique. Now, so hydrogen, and then what is de Broglie? A little careful, pronounce is de Broglie, not the Broglie. Broglie wave. He assumed 2 pi r total, 2 pi r, right? Radius. 2 pi r must be quantum. Quantum is n, depend on the n, something like that. Depend on the n1, n2, and so that's a he assumed. And then something like that. So that not only light but also electron is a dual property. Wow. Turns out, because we know electron is a particle, but since the de Broglie, we knew is a wave. So that wave and particle. Later, quantum mechanics says everywhere, electron is so weird. Okay. Anyhow, so that he was able to construct this. Once is that P is a momentum, m times v, and h is a Planck constant. So this is so important. The power, not the power, momentum. This is mv is something like that. Yeah, the same. Anyhow, yeah, this is so important. Okay, it's a wave. Once it's a wave, it should be like that. And then Heisenberg discovered if the product momentum and the distance, if it is less than, it cannot be less than that. So once it's less than that, we don't know. The answer is we don't know. No, that's not the true. Not that we don't know. It's uncertain is truth. Uncertain is the truth. Nah, we don't say we don't know. Uncertain. So uncertain is the truth. Either way. That's why Heisenberg uncertainty principle. Uncertainty is the truth. Okay, that's a quantum. And the Schrodinger, the wave equation, actually, we have a wave equations. The physics, this is potential. If there is a potential energy, the wave, because of photon energy, everything. This might be photon or energy, wave, whatever. This is wave equation. H, keep in mind, H bar is, I think, H over 2 pi. Yeah. So many times we have to divide it by 2 pi, so H bar. Anyhow, a little careful. So that's the wave equation. Now we look at the students. This lecture is too difficult, or it's okay. Somebody say something.
It's okay, sir.
Oh, it's
It's
okay.
good.
Yeah.
It's good, sir.
Yeah. This is already you have taken physics 1, 2, so very basic. I'm talking about a little bit information and good to know. So don't bother with some students, okay? 2 physics, this is engineering. I'm sorry if you feel like that. I'm sorry, but we need physics, okay? You will realize. So please be patient. Now, since particle is very complicated and 3D, and there is a potential, there is a potential energy, there is a between two atoms always attraction and repulsion, that potential energy, I think, yeah. Am I right? Something potential. So this is R, um, and potential energy. If it is too close, potential. If it is attraction, no, this is not the correct. I'm sorry. So this is R. Okay, yeah, this is correct. So if it is far, there is a attraction. If too close, then repulsion. Attraction and the repulsion. How to repulsion? Anyhow, I'm sorry. Suddenly, repulsion. Pushing each other, something like that. Okay. So so very complicated potential. But anyhow, general. There's a particle, and we like to think about it. Okay, we know that. This is the wave. I told you, wave. Wavelengths and constant, and yeah, de Broglie. This is de Broglie equations, and then well, general wave function without the u. U is 0. Yeah. So this is it. One dimensional, only x. So this is a second order differential equation. I think it's solvable. So second order, this is differential equation. This is general solution. AB, we don't know, but the sign KF. K, I think, anyhow. So then boundary condition, and we found, it turns out, equation sign. So if it is a particle, that must be a sine curve. Look at that. A is amplitude. I don't know, but so L is if it is a certain L, then wave. Okay. So A is actually we can figure out probability. Probability integrate wave function square. That's the probability must be 1. Somewhere we don't know. The probability is the electron is a wave, and we don't know where the electron is. The answer is uncertainty. We don't know is answer. That means we don't know the physics. No, we understand, but the uncertainty. So, but the only we can say is probability is 1. Yes, there is electron. So using this, we found A, and then plug in. This is the equation, wave equation, and then plot it, depend on the n. So we plot this n equal 1, n equal 2, etc., etc. This is not the orbit. No, don't confuse. This is a free box. So this is a wave. We don't know electron. No way to know. And then the probability says this is a possible electron. That's all said. This is a probability. Is it true? I don't know. This is quantum mechanics. This is wave. But there is only one electron. So according to quantum physics, everywhere electron, everywhere at the simultaneously, believe or not, everywhere. That's why light is coming. It's a reflect. That's amazing. And then the energy calculated. This is another one. This is not the atomic orbit. No, this is just the plane. Depend on the energy, ml, h, everything you can calculate energy. So, wow, this is a picture I found. Ah, Jesus. People are so smart. What is this? This is a copper surface, I think. Yeah, this is copper surface. Also, you can see the atom, copper atom. This is copper atom. And then this is iron atom. This is iron atom. So that there's a technique, even the laser, or even they can uh, move, so that they arrange the iron coral. They arrange it on the surface of copper. Then this is a probability of atom. Then somehow there might be some electron, free electron, always, everywhere. Electron, free electron exists, and it forms probability. Probability. All we see is a probability. Electron is so small, we cannot see. Electron is so small. All we see is a probability. That is amazing. That is amazing. So probability, actually, I think a quantum mechanic probability is proved. Nobody say that, but to me, it's probability is real. Believe or not. You can raise a question about this. This is so important. No question? Do you understand this now? Scanning tunnel microscope technique, STM. Now is a quantum number. Let's move on now. Okay. In order to discuss the electron in thermoelectric, yeah, that's we need to understand. Okay. So now is back to atoms and the quantum number. This is nucleus and electron and orb, something like that. We like to understand. Okay. So well, this is quantum physics, and a couple of things we have to understand: the Pauli exclusion principle and the quantum numbers. Principal quantum number is n. Fundamental principal quantum number n. That's what we call n. And then there is a second quantum number we call magnetic. This is second. And third is wait a minute, where is the third? fundamental. Oh, I'm sorry, second. This is second. This is third quantum number. This is fundamental and fundamental. First quantum number. So now is the fourth quantum number is spin. The reason we define the first, second, fourth is a state. They can be a state. Okay, state is very important. Now you keep in state. So each can be a state. So first is quantum number one and number one, obviously n equal one, fundamental. The first quantum number one, and the second, according to angular quantum number, that can be for first one, the L can be first one is 0 only. Okay, that is a very complicated the quantum physics, but you have to second quantum number. There are two possible angular quantum number. 3 is 0, 1, 2 possible, something like that. So that is no more than that, because of the state only can state. But the L equals 0, the second quantum number, there are also the 0 is 0, but the 1 is the magnetic quantum number. There are 3. 1 is 0 minus 1, 1 can be a state. So this is only possible state. 2 is 1, 2, 3, 4. So here is I made a table for you. Quantum number 1, first, second quantum number, third quantum number, fourth quantum number. The second quantum number, there are 0 and 1. And then third, 0, 1, 2. Fourth, 0, 1, 2. It all can be a state. The quantum number 1 is sometimes they call K shell, because they form the shell. L, quantum number 2. So if you look at this table immediately, quantum number 3 is another shell. This shell can be very close quantum number, but it can be everything is state. So if you degeneracy calculate, this is only 1. Here we have 1 and 3. Look at that. 1, 2, 3. 1, 3, 5, 1, 3. That's only can be a state. That's each state can be here. But the fourth quantum number tells Pauli exclusion. They say is a little very important. What they say, each state can have a different spin. So each state can have a different spin. So 1 minus, and then the other spin is possible because a different spin. That's why 2. So this is another state. So this is a final state. Force can stay no more than that, according to quantum physics. So quantum number 1, only 2 is possible. See that? And then if there is a more electron, then they have to move a second quantum number. They have to move second orbit, third orbit, fourth orbit. But what happened, these two is they call subshell. So, for example, 2 and 3 and neutron 3, then there must be 3. So 1 and 2 can be a quantum number 1, according to this. And then the third one, it should move to second orbit. It cannot be here. That's a Pauli principle. So these two energy, look at the energy is a huge in order to be 3. That's why this is become noble. This is very specific because the additional one require a lot of energy, That's a periodic table. If you look at the periodic table, where is the periodic table? The quantum number 2. Okay, quantum number 1 is hydrogen, 2 is helium, and 2 is helium. Look at that. It's a noble, very stable. 10 is the same. 18 is the same. So neon, argon is all kind of is a very stable noble, because in order to be another is very huge require energy. Look at that, 2, 8, 12. So that make a really make sense why the periodic table becomes so, where is that here. If you have one more, totally, the 3 is a totally different material, metal. This is a gas and metal. Sodium 11, 10. I don't like this. Yeah, neon, one more electron, proton. Actually, one more proton. Electron is nothing. Proton is lithium. Again, neon, argon, neon. Another one is sodium, magnesium. So just one proton make a huge difference. One, aluminum, silicon, just one, 13 and 14. That's even one proton make a huge difference. Sometimes property. And the second is there is some information. This one, the D4. Look at that. Copper FCC structure, cubic. AU FCC. Okay, so you can use maybe in exam the tables. So it makes sense, I think. If we understand the quantum number, so let's look at silicon. Okay, let's look at the silicon example. Silicon. Silicon is Z is 14. 14. So that let's look at it using these. Using these. Let's start. Okay. So 14. G is 14 is silicon. So that first, yeah, 1, 2, 3, 4, 14. And then n equal 1, n equal 2, something. Let's see how it works. So the first orbit, how many, you answer, electron can be a state? We have to have a 14. N1.
2.
2. Yes, thank you. 2. And then the next is the 8 can be 2 and 6. So quantum number 2, I think a 2 shell. Okay. L is a 2 shell. So maybe you better have a very close to 2 shell. The first shell is how many?
2.
2, yes. The quantum number 2 second shell is how many? Including
6.
6. 1, 2, 3, 4, 5, 6. So altogether, how many now so far? How many electron so far? Sum up.
10.
Say again?
10.
Yes, 10. So what is the quantum number is how many do we need more? How many do we need more?
4.
4, okay. So let's look at it. We have to go to quantum number 3 and first cell, second cell, third cell, because there are 3 shells. So the first shell, how many can stay, including Pauli exclusion? This is quantum number 3 now. The first shell. Come on, time is. you, 4 more. So first shell, how many we can have a state?
2.
Because the first shell is only 2, no more than that. So only 2. And then we have to move another shell. How many the last second shell, how many?
2 again.
Yes. And third shell, is there any third shell? Yes or no? Any electron in third shell? Yes or no?
No.
No, because we have a 14. So that is quantum number 3 we call is the uppermost orbit. Okay, that is possible Once you have energy, first this can become free. So this is a very important valence electron. So how many valence electron for silicon? Answer? How many valence electron? Valence is including subshells.
Maybe 4.
4, yes, 4 valence electron. That's very important to know in material science, okay? So let's move on. That's the way. If then what we can do is there is a name of it. I like the name of it. So first two is S. So S is, and then there are two. The second one is, I'm sorry. The second one is 2S. Oh, no. First is quantum number. I'm sorry. First, the quantum number, there are two. Let's say it again. I have to start with the first quantum number. The first quantum number S, how many? 2. Second quantum number S is 2. Second quantum number P. Next is P, name it. P is 6. And then third quantum number S is 2. And the third quantum number next is a P and D. P is 2. This is the silicon configuration. (14). Yeah. Silicon, this is the configuration. Just we got it. Okay, 1s2. The first is quantum number 1, 2, 2, and that is a number of electrons. So okay. Let's move on. Take a break. I like to take a break. See you 10 minutes. Hi, I'm back. So a little bit more atomic structure, nucleus, and electron. So it could be more than one, but anyhow the same. So huge nucleus is so small, and inside is nothing. There's no any element because this is the smallest. And then quantum, there's nothing inside. So that electron can form the quantum mechanic. It can be anywhere. So that as you see, the surface is just you can see everywhere. It look like it's not everywhere, but that's the quantum mechanics. This is a probability. This is a probability we see according to an everywhere surface. So that light coming and reflect. That's what we see. What happened is inside is perfect. Nothing is bothering except that the last one. Inside is so vacuum, perfect. So if anything outside, no, because of something collision is outside is all different story, frictions. So usually it's a electron particle rather than wave, but mostly particle behavior. But inside is a perfect. So we have one more things about the speed of light. I like to let you know, according to measurement, this is about 10 to the 8 meter per second. It's a huge speed, is constant. That's so important. This is constant. Anything else is relative. Depend on the speed. So you are flying with the speed according to Einstein, the theory of relativity. Something change, time change, and the distance change. It depends on the velocity. According to universe, the Earth, Sun, Earth is moving. Everything is moving. So nothing is constant as long as it's moving. Even galaxy is moving. The universe is expanding. The only constant is the speed. From that, Einstein able to Einstein's special relativity and even gravity, he able to calculate. And the gravity is a space relationship. So space is changing with the gravity. The experimentally it's proved. So high gravity, there is the distance 1 meter is different. 1 meter is not constant because on Earth, yeah, maybe, but depend on the speed, depend on the gravity, the distance is nothing. Time is different. The flying, we measure the time over the years, the jet plane, the time atomic time is different with the Earth ground time. Small, but depend on the velocity. Time is changing, space is changing. So 1 meter is nothing. So only we measure 1 meter is speed, velocity, and time. Then meter. Time is changing also, but anyhow, everything is changing. So near the black hole, the space is so different. Okay, the Earth can be a peanut near the black hole. Amazing. Anyhow, the speed is constant. Now, two double slit electron is shooting, and turns out there is an interference pattern, which means a wave. Okay, if it is a particle, it cannot be an interference like that. But if any disturb, this is a highly vacuum, nothing is interfere, and then yes. But if something interfere, some air, no, they don't show the interference because of disturbance. Okay, so this is wave particle, but sometimes a particle because of some interference. So this is evidence of experiment. Look at that. This is wave. All evidence. Particle, no, electron is wave. Electron is wave. So de Broglie is correct. Okay. Now there is an experiment after de Broglie using laser and shoot laser, and they found interference. So interference means a wave. This is a proof of a wave. So no question. Electron is wave and the particle. Okay. And okay, let's go back now. So now is a more band theory surface. This is we discussed now. The atoms of silicon, the bond. Okay, there is a three types of one of bonding is covalent bonding is the 4 electron. This 4 electron valence electron share with the others because the uppermost electron is easily sharing forms the covalent bonding. This is silicon, actually. So silicon is most used, and then what happened? This is an isolated atom. There is a p type, s type. You know that sp. We said soft shell. So that we understand this is the energy level between the quantum numbers or between the subshells. But what happens if it is a crystal, solid state physics? It's very similar to the atoms. This is atoms. and this is now crystal. Again, there is the valence band and the conduction band here. There is a gap. We call conduction band bottom, valence band top, edge. So there is a gap. Okay, that gap is a very important property. Silicon is 1.1 electron volt gap. So different material has different gap. Because this gap is the conduction, the valence is a kind of atomic state, but the conduction is free. Electron is free. So in order to work with thermoelectric, it should jump from valence electron to conduction band. In order to do that, they have to overcome the band gap. So band gap is so important to become free. Okay, this is atom, but now is crystal talk about. I think you have to understand or raise questions so far. This is now we talk about the solid and the band gap. Oh, you should be genius, no question. I studied 20 years, a lot of questions, but seems you understand. Anyhow, I'm not smart, so you are smart. Do you have any question? Genius? Okay, let's a little bit move on. I'm not kidding. You know, I was not good students when I was college, unfortunately. No, fortunate, unfortunate. My score is not enough to go to graduate school. So I had to go to after graduation college, I have to go to again college 1 year and take 10 courses to demonstrate I'm good. I got all A. Then I was admitted to University of Michigan. Is that the smart students? No, I don't think so. Okay. So we understand that. So don't discourage if you are not smart, okay? Smart is not required. And doping. So say this is the atom and something we understand valence at, valence band at, conduction band at bottom, top bottom, that is band gap. So still there is a quantum number n23, the ultimate uppermost valence band, so we understand, and then become free. This is free. So what we can do is, this is a silicon, intrinsic silicon. Is that right? The name? Pure silicon. And now we like to create, okay. What happened is here's the electron. If the electron become free, yes, it's possible. Then electron is moving around. Then what happened is there is a hole. Okay. This hole is the same charge because of electron it was, and then this is ionized. neutral, but now is ionized. And then some electron can replace. So this hole is moving, electron is moving, hole is a plus, hole is moving, it's canceled. Look at that, electron is moving this way, okay? Hole is moving this way. Do you think you have current? Yes or no? Because current direction is, this is current direction, this is current direction, same direction, hole. So the sum is 0. That's the problem. I think you have to really understand. I'm going to make a quiz about this. You should understand. You have to say something again. I will repeat until you understand. Okay, this is intrinsic pure. There's an electron. It can be a free. Then holes. Then this hole, this electron can substitute, and then hole is moving around, same as electron. So that there is no any benefit of current because of hole is moving, electron is moving. So something we have to do without the hole, just the electron is moving. Yes, we can do it. That's a phosphorus. Silicon is 14. What is a phosphorus? Let's look at it. Atomic number. Yeah. Silicon is 14. Phosphorus is 15. One more. Okay. So if you doping, there's a lot of doping technique. With the temperature high during the solidification, there's a doping technique. And then there are 4, 1, 2, no, 1, 2, 3, 4 silicon. And this is 5, one more. One is just without any position. So in this state, very easy to become free, small energy and become free without the hole. Do you understand? So this is 15 valence number, one more electron. It is easily become free. This is the doping phosphorus on silicon. So that we can create the electron without the hole. That's good. Only electron moving, then current is flowing. Same way, this is an N-type. Electron is an N-type semiconductor. N-type. Hole is moving is P-type semiconductor. So what is a gas? A boron, a number of valence electron number. And gas.
3.
No, it's a 14. But the valence, there is a 4 valence number, 4 electron. This must
Right.
be
So,
3, valence 3.
thank you.
Valence electron 3. So not total, but the valence is important. Valence number is important. That's why, where is that? Yeah, where electronic, there is this is 3, boron is 3, group 3. So group 4, group 5, there is indication, group 6. This is a valence number, group 2. For silicon is group 4. So you can tell me now. Phosphorus is what group number? Come on.
The fifth.
Phosphorus, group number.
5.
Sulfide, group number. Sulfide, group number. Say something.
6.
Bismuth, group number. 5. So it sense, okay. So we can choose element for doping. Doping is important, okay. So that we have a phosphorus, boron, all kind of business to have a N-type, P-type. That's why semiconductor is good for thermoelectric. Okay. What time is it now? Oh my God! What time? No, 8:42. Oh, so we have time. Oh my God! I thought the 9:42. So we have a group number 3, 5 element. So this is all possible semiconductors. You know what I mean? We need a semiconductor, all kind of possible material future. I told you, right now technology is GT is about 1. I said that in the future, what did I say? GT number in the future, immediate goal. Come on.
3.
3. It can be 5, but the immediate 3. I think I cannot wait until the end of semester. I just found it. Okay. This is 2021, last year. Anyone, the element SN? If you remember that, you are super good. No one remember, right?
Is it antimony?
No.
What? Silicone?
No, it's okay. I think SN, let's look at it. Tin. SN here, yeah, is tin. You know, the same as you, if you have question, you can look at the table of the book. SN tin. SE is, what do you think, SE? Tin is SN. SE, selenium, SE, okay? So, I think you just relax, nothing, this is nothing to do with the exam, okay? Just relax. So, recently, this group, I think most is Korean. South Korea. Because I'm sorry, I'm gonna retire and go to Seoul, South Korea, and live there. I will not come back. I like Korea. Okay. Anyhow, I'm happy retiring and no more study because my wife, I'm so sorry. You know, I'm not good husband. You know, my wife, I have to look at my family, my wife. We're gonna go travel, having restaurant, music. She is a pianist. She majored the compositions. We never go to the music concert. I'm so sorry. I'm almost crying. I so focused on the studying. I'm egoist. I am egoist. How to spell egoist? So what I decided, I retire. No more writing paper. No more paper. And relax. Okay, in Korea, a lot of Seoul is now is a so rich country. I left 45 years ago. My daughter is 39 years old now, living in Los Angeles. No, go back. So this is team is developed. They call polycrystal. Usually crystal is good, but is expensive and it takes a long time to fabricate the crystal. Okay, so we look at the polycrystal because inexpensive and quick manufacturing. Poly is the crystal. This is a micron, so look at the micron. This is a boundary, gray boundary, grain boundary. So that they did it inexpensive, and look at that. The grain boundary. So it's not the crystal. Crystal is there's no grain boundary. Everything is the same. But this is a crystal, but there is a boundary so small. And you know, this is the actually the laser and the shoot, and then they can confirm the boundary. Do you understand? The boundary actually there is some boundary and the shoot laser, and they can figure out like that. Okay, intensity. So they use a technique and figure out the confirm, and then this is a GT value. This is temperature. So depend on temperature, they have measurement 800. Can you read for me the GT value? Come on, please. What is the GT value for 800? Please read for me, students.
Three.
Wow. This is 2021. Already they got the 3. Not in 20 years. No, now. Obviously, this is a lab, but it commercialized, it takes 10 years. But anyhow, I told you. Amazing. Amazing. Okay. The using the grain boundary we will discuss later because it is necessary. Electron is moving and then boundary. Okay. And not only electron, phonon, how can I say? Photon is electron. Electron is same as a photon. Phonon is vibration, lattice vibration, small vibration is a phonon. Okay, it's a vibration, but name, because it's something like a photon. So photon, how can I, pH, photon, phonon, phonon is bounded. So phonon is block, electron is passing. Usually it is the same way, electron passing, phonon passing, so no control. But this nanotechnology, we can control the electron passing, phonon blocking. That's what they want to do it. Nanotechnology, thermoelectric, figure of Mary. This is a nature. You know, nature, science is the best journal. You know that. Two journal, Nature and Science. Nature is British. Science is American. Best. These two top journal is the best. If you have a publication in Science and Nature, it's a great. You can be offered MIT. Okay. So this nanotechnology, and right now they able to get the GT3. So I have to tell you immediately. Let's move on. That's so important understanding. Okay. Here, back now. I'm so tired. The K, again, this is we will discuss, is consists of electronic thermal conductivity, lattice thermal conductivity individually studied. Okay. So, and we discussed this is known. The heat flow is Peltier cooling and conduction. And the electric field is current and the Seebeck. This is a voltage, same as, not the exactly. So this is a thermoelectric, and then a Broglie relationship. You remember Broglie? And actually, we use K, not the thermal conductivity. Don't confuse. K is inverse wavelength. This is wave number. I think we need a huge study. It's so weird. And when we look at in terms of H bar K, energy is kinetic energy. Hello, I'm 수업하는데. Okay. So this energy in terms of wave number, I think you have to understand that. Okay. So everything is moving. Now, the electron is velocity, but so many electron, it forms a average velocity. So wave, very close. It it is kind of a particle. So this is now we call average velocity. So electron is nothing more than very close to average velocity. And still we can use a particle theory. And it turns out something very interesting. I think if you follow, there is some kind of mass, not the real, in terms of K and E and H. This we call effective mass, because M is absolute mass, but energy can be anything, because when the electron is moving, there is atoms. There is atoms, so complicate energy. Electron is moving. The potential we call potential. So moving is very complicated because of potential of atoms. But when this complicate, if we use effective mass star, then this is mass of star, assuming and moving. Wow. Okay. So it is a so smart way, because we use effective mass instead of electron mass. Electron mass is very clear. So effective mass, electron mass, what is the relationship? 0.86, something like that. But still, in terms of electric mass, electronic mass, or effective mass, experimentally we can figure out, and then simply we can calculate. This is so smart. Okay, so I think when we do that, I think you maybe follow. This is important. This is end of A. Now B. So that I will go over, but we come up with now in terms of energy, because mass is complicated. And then instead of electron mass, we use effective mass. But this is very specific density of state effective mass, MD, defined. This is a real mass. Okay. And not the real, but this is the directional mass. So that we can use this, and if we assume this is electron, well, we can do that. And if it's cubic, the same, very simple. Then XYZ is the same. Then it might be a ME, something, electron mass. Then just the energy. We can calculate the density. So we call density of state. State, I told you, is very important. We can calculate state is very important. And now in terms of K, because this is so complicated structure and crystal, if we use a wave number, we can, this is in terms of wave number, space, K space. I think you read, actually I'm telling you, you read, we convert the K space and then express whatever. So we discussed the density of state, effective mass, and also the distribution, electron distribution, with the temperature and energy. It is a kinetic energy or whatever energy, and there is Fermi energy. That's so important. The distribution is a function of energy, electron distribution. The zero is equivalent, same temperature. But the real is there is a temperature gradient. This is equilibrium, thermal equilibrium. And Fermi distribution, this is the distribution, yes or no. There is a electron or no, depend on the temperature, Fermi distribution function. This is we can use to estimate Fermi and the density of state that indicate the number of electron. Wow. From 0 to infinity, energy from 0 to infinity. Well, I don't know, 0 to infinity. Then that's the number of electron to figure out. So number of electron is electron concentration per unit volume. Okay, so plug in, we have an expression, density of state, the Fermi distribution. So plug in, and this is a number of. So suppose we have some material, but it's constant, everything is constant. But Fermi is, I don't know, but integrate energy, because once you integrate energy, it will disappear. Do you think you can calculate the number of electron for the material once you have an idea of the effective? Yes or no? Maybe yes, because the distribution is known, so that we're able to calculate. But this is equilibrium, same temperature. It is non-equilibrium, is complicated. Okay, so I like to homework. This is a rover, Mars rover, and the JPL, Jet Propulsion Lab, NASA JPL, same, almost. They constructed Thermoelectric. This is plutonium radioactivity. Plutonium I discussed. It's for 60 years we can use as a power, and then Thermoelectric, and then the design heat sink, and then they all need a 110 watt for the rover, Mars rover, and they construct it, and then they have to decide the ratio RL of R. What do you think they used, JPL? Tell me something. Hmm? Some papers, and they say one. I'm not quite sure, but they say one. This is because they have no idea of optimal design. This is incorrect. Okay, you have to optimal design, calculate what is the reduced R. I think it could be depend on the GT value. If GT is 1, this is about 1.4. If GT is 3, then R of R is 3. I told you. Homework. I'm gonna post homework. It's a simple, very simple two line of sometimes. So pretty soon we're gonna have a quiz. I think this is you have to study hard for quiz. How many? 1, 2, 3, 4, 5, 6, 7. 7.
6.24 and 6.25 have already given us.
Oh, already given? I'm
Yeah,
sorry.
yesterday.
Yeah, we just submitted those tonight.
Yeah. Then yeah, take it out. Sorry. Okay.
6.525 as well, sir.
Yes, sir. 6.25.
Oh. Oh my. So total is 5. Okay. Total is 5.
You're going to be posting the quiz as well.
Say again?
Are you going to be posting the quiz, the second quiz as well?
I will think about it. I haven't decided. I'm thinking, okay? So just work on the homework and probably we will have a quiz. Okay. Any question? Okay, see you next hour. Bye.
Thank you, sir. Bye, sir.